Hi, welcome to today's Cosmic Pie podcast. So I'm your host, Wayne Barkhouse, and here I'm with
Robert Moore, nice to meet everybody.
Hi, Robert. So let's kind of do the introduction here. So this is a podcast that focuses on topics related mainly to astronomy and astrophysics. We also do physics in general and science to go more general than that typically.
Right.
We are broadcasting live from the campus of the University of North Dakota. And in particular, we're in the College of Arts and Sciences and the Department of Physics and Astrophysics. I'd like to mention also the fact that we do have a live chat that's running. So if you have any questions throughout the podcast, if you're here live with us, of course, feel free to send those questions in. Also, disclaimer. I hate to keep saying that. But
Well, we need to mention it.
right. So anything that Robert and I say during the podcast, of course, is our own personal opinions and not necessarily those of the university, the college, or anyone affiliated with it thereof. How's that, Robert?
That sounds like a good disclaimer to me. Short and to the point.
Short and to the point. Now, Robert, we're actually looking at each other, and it
Yeah.
looks good on camera, right?
I guess so. I mean, we got a complaint that when I was
Suggestion,
looking over
a
at Wayne,
comment,
okay,
not a complaint.
okay. When I was looking over at Wayne, I was looking in the opposite direction, so I had to switch around the cameras because I don't know of a way to reverse, flip them, mirror them. So
You were just taking the long view, right? Because
that's yeah.
the Earth is spherical in shape, so the light would eventually come around, right? That's it.
Eventually, right?
Unless, of course, you're a flat Earth person. Are you a flat Earth person?
I am not. In fact, I'm so anti-flat Earth, I will not even engage with such people. They claim they're willing to be convinced. Sorry if you happen to be one. I apologize for this statement, but I'm going to make the statement. I have not met one yet that was willing to be convinced. So,
So, Robert, and when you think about the flat Earth, what is the explanation when you see pictures that were taken from the moon of the Earth and the Earth's round in appearance? What do they say about that?
generally, they say that's a fisheye lens, that it's a macro lens so that it induces curvature where there is none.
But a fisheye lens, you would notice that everything in that image would be affected by the fisheye lens. How come it's just the Earth, the one part of the sky?
And they have no real good answer for that.
Okay, just interested in their arguments a
Right.
little bit there.
Yeah.
So it's kind of
It's some of the mental gymnastics is really impressive, actually.
right. Well, these images, when you think of Apollo 11, that was taken in 1969. That was before Photoshop was invented.
Right.
And so it's not like you could Photoshop that in
There you go.
July of 69. So
As a show I recently pointed out, they go, oh, well, the moon shot was faked. And it's like, yeah, except all the shadows are actually parallel when you actually draw lines in through them and everything. And the only way they could do that was if the light rays were parallel, which would have required lasers. And back then in 1969, lasers were kind of like computers. They took up rooms,
right.
Yeah. And to get multicolored ones, well, no, they had pretty much red.
Yeah. Can you imagine? You think about the first computers, how much space they took up.
Right.
I mean, number one, colleges, universities probably couldn't afford them. So it'd be government agencies like the military, maybe the weather people could afford the large computers, this kind of stuff. And that would take up huge rooms, right?
Well, had a discussion with a student about these nice little devices. And somebody did a calculation. If you did one of these devices, which is a cell phone, by the way, with vacuum tubes and everything, just the physical space that the vacuum tubes take up, they would have to have a volume of roughly 3 city blocks. So your cell phone has the computing power of a 1960s computer that would take up 3 city blocks.
So the old computers would have vacuum tubes in them.
Right.
And like the incandescent light bulb compared to the LEDs that we have now, the incandescent light bulbs, you can feel the warmth. In fact, if one of the bulbs blows out and you go to change it immediately, you can burn your hands on it if you're not careful. So a lot
Having
of
done that, yes.
So a lot of the energy that's being consumed by the functioning of that light bulb, a significant amount of it was just being thrown off in infrared light, which is useless to our eyes.
Right.
So that's wasted energy. And now with the new design light bulbs, a lot of people are out there complaining about them. But those LEDs I mean, you can touch them when they're on and you don't burn your hands. There's so much of that energy is fine-tuned or allowed to go manufactured in a way that it comes out mainly in the optical rather than in the infrared.
Right.
I mean, that just saves energy, right?
Just
So
saves
overall, that's a tremendous amount of saving. If you look at every light bulb in the world, if it was that type, how much energy would you save versus if it was all incandescent?
Yep. It's impressive. It's a nice savings. It's, and I will point out that those bulbs still get warm to touch. So there's still some waste energy. So, I'll throw in a little plug here. Come join us. Maybe you'll be the one to discover the next generation of light bulbs that does better than the LEDs even. And all of a sudden, there's even less heat energy being wasted.
So the next generation of Thomas Edisons.
Absolutely. Come join us. Yeah.
So the vacuum tubes in the old computers, you imagine the amount of heat that were generated. That's what I'm getting at.
Yes.
So they must have had a real air conditioning type of system hooked up so that the thing could survive running any length of time.
Well, they talk about, if you go back and read the old accounts of computers, they talk about how hot it would get in those rooms when they were running. So, yeah, the 3 city blocks, you would have to flood the thing with like liquid nitrogen to keep the thing operating because it would just melt from the heat it produced.
Well, if you had a computer in a large, let's say, building that occupies a lot of workers, you'd want to put the computer in the basement, and then in the wintertime, if you're in a cold weather climate, then that heat would just propagate upwards through that building, cut down on your heating costs.
Oh, hey, I like that idea. Maybe we need to switch back to...
So at least you're using some of that heat in a good way,
In
right?
a good way, right.
So, I mean, yeah, so that helps. But, we talk about energy considerations, Robert. One of the kind of things we like to talk on this podcast, of course, is really big fundamental issues in astronomy and astrophysics. And I don't think there's arguably no larger fundamental issue that we're trying, or mystery, if you like, that we're trying to unravel today is one that involves energy, and it's known as dark energy.
Right.
Now, that first part of the term dark, that just means, in some sense, mysterious or unknown. In fact, we know that there's energy out there because we can observe the consequences of the universe being filled with this dark energy, and we'll talk a little bit later what that really means. But as knowing where it actually comes from, what's the origin of this energy, these kind of things, which is ultimately, as a physicist, you want to know.
Right.
So we don't ask the question, why does something look the way it is? Why does something exist in the first place?
Right.
There are a number of questions that we keep going down the tree, if you like, getting to the root cause of whatever we see around us, the fundamental nature of things.
We see these consequences and we like to ask why? What's going on? So...
yeah, or even how come? How come it's that way and not some other way?
Right.
These are, basic issues. And that, with the dark energy is like, where does that come from? The dark energy itself.
What is it? For that matter?
We can, like I said, we can measure its consequence. And we've done that, since the 1990s. In fact, the papers that were published, one was in 98, I believe, and the other one in early in 99, that showed observational evidence for the existence of what we call an accelerated expanding universe.
Okay.
So to kind of start back, in case people haven't watched all the podcasts or haven't thought about it in a while, back in the 1920s, one of the things that was done was a paper that was published by Edwin Hubble and collaborators, which basically showed evidence for an expanding universe. So prior to that time, people thought the universe was static. Why? Well, one thing is it's the most simplest type of universe you can live in. Why complicate it to make it either contracting or expanding? Let's just make it static.
And I will point out, if I'm not mistaken, general relativity pointed to the fact that it needed to be either contracting or expanding, but even Einstein himself didn't like that idea, so he tried tinkering with general relativity to correct, as he would put it, for that.
In fact, you can go even further back in time when you think about that particular point of a static universe versus a non-static universe. Even Newton had problems with that idea. Because if you have mass spread throughout a finite-sized universe, the combined gravitational pull will bring that universe together.
Okay, right. Yeah.
You see? So the way around it, and he wasn't quite sure, is he hypothesized that maybe the universe is infinite in extent. And if it's infinite in extent, then matter spread everywhere forever. And so it kind of cancels it all out. And that turns out when people looked at it, doesn't really work either.
Oh, right.
So
Because you would get clumps. of stuff. Right.
So Einstein was kind of finding himself in that same position, is try to match the theory with observations. And astronomers at the time, this is, let's say, in 1915, for example, in late 1915, when Einstein basically had the general theory of relativity
Right.
and was, setting to publish it and so on. I mean, at that time, astronomers thought the universe was static. In fact, the universe itself was just the Milky Way galaxy. There was nothing
Right.
beyond our own galaxy at that time.
Even things like the Andromeda Galaxy, which was known and seen and observed, were thought to be just nebulae inside the Milky Way.
Right, and one of the old terminology for the Andromeda Galaxy is the Andromeda Nebula. And that's what it comes from. In fact, people, because they didn't know the distance to the object, some people argued that the Andromeda Galaxy, what we see today as the Andromeda Galaxy, really was just a solar system in the act of forming.
Oh, I didn't know that.
Yeah, so the bright part, the central part, the bulge area of the Andromeda Galaxy would be a newly forming star.
Right.
And the disk-like, which is the spiral arm structure of the Andromeda Galaxy, would be the protoplanetary disk of that newly forming solar system.
Okay.
Now, if
I
you
had
don't,
not heard that.
yeah, so if you don't know the distance to the object, how do you know for sure? You don't,
You don't.
right? I mean, you have to be clever and think of some other ways. So once we discovered a way of measuring distances to relatively nearby galaxies, this is using the Cepheid-period luminosity relationship. So this is the idea there are certain classes of stars, these Cepheid variable stars, that change in brightness with time.
Right.
You can actually measure it. You can take photographs of Cepheid stars over the course of several nights, let's say, if you have clear weather, of course, that for that long of a time. And you can measure their change in apparent magnitude, their apparent brightness.
Right.
And what we discovered is that these type of stars follow a fairly well-known relationship known as the period luminosity relationship, where their period of variability, so imagine the best way to do it would be take the time in which the star would appear the brightest, because intrinsically it's going to be faint, right? If you're looking
Right.
for something that's in a galaxy, depending on what you're using to observe at it, it's going to be faint. So you want to look at peak brightness. So you calculate how long does it take a particular Cepheid star to go from peak brightness back to peak brightness again. So in other words, it goes through a minimum and then back up to maximum brightness, and then that whole cycle just repeats over and over and over and over again.
Right.
So for Cepheids that were close enough that we had another way of measuring distances to those Cepheids, what we discovered was for Cepheids that have a long period of variability, the time between maximum brightness and maximum brightness, let's say it's 50 days instead of 5 days, for example, those Cepheids with the longer period had a greater average luminosity.
Brightness. Right.
And so so intrinsic brightness, think of wattage like a light bulb, for example. So then you can compare, and based on the period of variability of Cepheids that you measure, you then use that relationship to get the average luminosity, and you just have to compare it to what is the average brightness.
Right.
And we know that for a source of light like a star that's emitting light in all different directions, that light will fall off as 1 over the distance squared. Right. So if you double the distance to some star, let's say, maybe you move away from it in your starship, in the future. If you double the distance, then that star is going to only look 1/4 as bright, or 25% as bright.
And I will point out you can do an experiment with this yourself by simply taking a flashlight, and you can see rather readily that the brightness drops off as you walk away from it. So
that's right. Yeah. So once we could use a technique like that to estimate distances, then we knew there was much more to our universe. There were than just the Milky Way. There were other galaxies external to the Milky Way. And so at that point, and people started saying, okay, well then what is the universe like? Like how many galaxies are there? How are they, where are they located? How are they distributed in space? Are they all moving in one preferred direction? Or do they all have random motions? All this kind of stuff.
Right.
And as we talked also in the past in different podcasts, you can calculate what is the average motion of a source of waves relative to us. In this case, of course, the waves would be the light properties of these objects. And when astronomers first went out and measured what were the motion of those sources of waves, they discovered that except for ones that are really nearby in our backyard, in what we call the local group, all other galaxies, so everyone beyond the local group, all are moving away from us. Right. They have what's called a recessional velocity. In other words, a redshift, as we say in astronomy.
And that gets greater the further away they are.
That's right. So the greater the distance between our galaxy and some other galaxy, the more space obviously is between us. And if space is expanding at a certain rate, then that distant galaxy, the further a galaxy is away from us, there's more space. So the more that galaxy, the faster it should be moving away from us because of that expanding intermediate space, if you like, intervening space. And so there's a natural relationship that gets set up that the greater the distance, the faster the galaxies are moving away from us.
Right.
But it doesn't imply we're at the center of anything.
Right.
Because you could transport yourself, if you could magically do it, to another galaxy 10 billion light years away, and you'd measure the same effect all around you, that all other distant galaxies were moving away from you, and the further a galaxy is from you, the faster it's moving away.
Right.
Now, the most simple explanation of that effect, which was published by Edwin Hubble, mainly the main sort of publisher of that.
Coming back around to where we started.
Yeah, is the fact that the universe is expanding, right? Now, there are more complicated ideas you can come up with, right? But they're all, very complex, and the simplest thing is that the universe is expanding. And in science, it's this idea of Occam's razor. We tend to look first at things that are the simplest, and if that doesn't work in our explanation of the facts that we see, whether through observations and or experiment, then we make them a little bit more complicated and build up the complexity.
Right.
You see? But the simplest explanation to the so-called Hubble's law, or Hubble-Lemaitre law, as we say today, is the fact that the universe is expanding. So you have an expanding universe.
Yep.
Right? And so what was discovered in 98, 25 years ago approximately, is that not only is the universe expanding, but that expansion rate is speeding up. It's accelerating, as we say. It's as if, and maybe this is so or maybe it isn't, there's this anti-gravitational force that permeates all through our universe, pushing galaxies away from each other. So we know gravity, I always joke and say, unlike ice cream, it only comes in one flavor. It's always an attractive force. So here's something else coming along that's not gravity, so don't get confused thinking it's gravity per se, but it has the effect of anti-gravity, pushing things away from each other. So it's as if there's this energy field, for lack of a better description, that's everywhere through the universe. And this energy field somehow is responsible for causing matter to move away, to repulse each other, or to be repelled from each other. Now, what is that energy field? If it is an energy field, that's the big mystery today.
Right. And so, again, we've come back full circle to what we started talking about. So, yeah, there's this energy field we don't understand. And so we call it
dark energy.
Dark energy.
And one of the things that people, some people, not everybody, but when you mention energy, people say, okay, now how can I harness that energy and funnel it into my car? Because gas prices are relatively high, depending on where you live, of course. Can I solve the economic issues of high cost of energy by using dark energy? It's everywhere, including in the room that we're broadcasting live from, including maybe if you're in a room watching this, it'll be all around you. If you're outside, it's all around you also.
Right.
But then you calculate what is the influence on things that we can see. That's how we discovered dark energy to begin with. And then you can estimate what is the density of that dark energy. And it comes out to be an extremely small value.
Right.
So when I say that, you should say, what is the value?
So
right?
What is the value?
Thank you. And so the density of dark energy is about 6 times 10 to the minus 10 joules per cubic meter. 10 to the minus 10 joules per cubic meter.
That's tiny, folks.
That's really, really tiny.
Yeah.
So it's, you'd have to harness a lot of that dark energy over a huge volume of space in order to funnel it into somehow a useful way of using that energy.
10 to the 10th is 10 billion. So 10 to the minus 10 is 1 over 10 billion.
Yeah.
1 divided by 10 billion. So this is a minute amount of energy. You produce many billions of times more energy when you sneeze than this energy field is.
Well, then the thing is, and then people say, well, if it's so small, why doesn't it even affect the universe? Because the universe is
huge.
It's large. So this is the amount of energy per cubic meter.
And there's a lot of cubic meters in just the solar system, much less the universe.
Solar system is on the order, 10 to 38 cubic meters, if you want to use Neptune as defining the sort of the radius of the solar system, right?
Right.
And you assume it's a perfect sphere. So we all know from simple geometry, what's the volume of a sphere, Robert?
4/3 pi r cubed.
Right. So you take r and you cube it. That is the semi-major axis of Neptune, and you multiply by the other factors, which really don't, changes a little bit, but not huge amount.
Right.
You come up with a fairly significant number. Now imagine for the whole universe what that number would be.
And that gets into a point. We astronomers tend to work just with powers of 10 because the rest of the number doesn't really matter.
Yeah, that's it.
That's because the numbers are so huge.
Well, the joke in astronomy was always, if you know something within an order of magnitude, you're doing pretty well.
You're doing well.
That's kind of the joke a lot. But
Yeah.
anyways, so why we mentioned dark energy, number one, it's one of these topics we always wanted to come back to and say a lot more about it. But the other thing is it's been in the news lately. So if you want to go to our first slide.
And this is probably a picture that everybody's seen.
Yeah.
Or most people have seen.
So what you're seeing here basically is images of galaxy clusters. So there are 3 of them. What you'd see in the optical is the bottom panel. And what you see in the X-rays is the top panel. Now, what's new here, because we've seen galaxy clusters, so just to remind you what a galaxy cluster is, these are systems that contains upwards, to thousands to tens of thousands of galaxies, all confined to a relatively small volume of space, all attracted to each other gravitationally. So they're orbiting what we say the center of mass of the system.
Yep.
And so when you look at these galaxy clusters, in the optical, you see individual galaxies, but if you look in the X-ray, what you're detecting is really hot gas.
Mm-hmm.
And so this hot gas, it was discovered when we've got our first X-ray telescopes up in the space. If you have an X-ray telescope and it's in your backyard, it is useless because the X-rays get totally absorbed by the Earth's atmosphere, mainly the ozone layer. And so if you want to see X-rays from sources beyond the Earth, then you have to get your telescope into space. So when the fairly good X-ray telescopes were first launched, I guess it would be in the 1960s, the first real good ones that started, and into the 70s and beyond. What we realized eventually was that these galaxy clusters, and almost every one of them, have this very hot gas. When I mean by hot gas, think of tens of millions of degrees.
Right.
Now, it doesn't matter what the temperature scale is, whether it's this Fahrenheit, Celsius, or Kelvin. When you're talking about tens of millions of degrees, it's roughly the same number.
It's roughly tens of millions.
Don't get hung over the temperature scale for this point. And so if you have a gas that's this hot, and let's say I had hot gas like that, and I had them in some kind of a container, and I passed it to Robert, and I said, Robert, would you hold this for a while? I'm going to go to lunch.
No.
Yes. Why? Because one of the things that gas would do at that extreme temperature is emit lots of X-rays.
And expand.
Yes. And so what's happening in these galaxy clusters is you have lots of this hot gas that emits lots of X-rays. Now, the technical process at work here is known as thermal Bremsstrahlung radiation. But just think of it as the source is so hot, it's emitting light in all different wavelengths, but a lot of it is coming out at the very short wavelengths that represent X-rays. And this hot gas is extended throughout the cluster. Now, there's more of it near the center, okay? So there's a greater, if you like, luminosity or emission coming from the center than it is on the outskirts. And so the hot gas itself then is an extended source in most of our telescopes, but that depends on how far away the cluster is, what is the resolution of the instrument you're looking at. But in the images you're seeing here, the X-rays are in the top panel. So the corresponding galaxy cluster in the optical is right below it. Okay, and that's why you see these colorful blobs. It's just been color-coded to make it easier on the eye to see differences in the emission of the X-rays, where it's greater and where it's less. So changes in the emissivity, as we say, of the galaxy cluster. So it's more of it coming out in the core regions than it is out on the outskirts per cubic volume of space, way to think about it. Now, the type of instrument that was used to make these particular observations is the new Rosetta spacecraft. And what it has done is a pilot study looking at a certain specific region of the sky. And from that pilot study, people are analyzing the galaxy clusters that they detect and then matching them up to what you see in other wavelengths, like the optical, which is the matching you're seeing here. Now, for this type of telescope, the galaxy clusters we're looking at are resolved sources. That is, they're not point sources on the sky. Right. They have structure to them. They're extended, as we say. Okay?
Right.
So that allows us then to find galaxy clusters that otherwise maybe they were missed, or because we didn't have a good survey looking for them in the optical or the infrared or whatever. But in the X-rays, you just look for these extended sources. So eventually what's going to happen is that this eRosetta spacecraft is going to do an all-sky survey at X-ray wavelengths, and it's going to be more sensitive, be able to see clusters that are further away or clusters that have less gas in their region, in their interior, if you like, than what we've seen previously with our other past generation of X-ray telescopes.
Right.
So it should accumulate or compile a much larger sample of galaxy clusters, okay, based on the X-ray detection.
Okay.
And what you can do with that is then if you see an extended X-ray source on the sky, then there's kind of two possibilities of what it could be. It could be a nearby individual galaxy that has X-ray sources within it, and then together you see this extended emission. Or it's a galaxy cluster.
Right.
And those galaxy clusters would be at a much larger distance away than an individual galaxy that looks like an extended X-ray source that happens to be nearby to us.
Right.
So therefore, almost every extended source, as they say, modulo the nearby couple of galaxies that would be in it, the catalog that you generate with an all-sky survey will be dominated by galaxy clusters.
Makes sense.
Okay?
Yeah.
That's the first thing to think about. Now, the other thing to note is that the abundance of these galaxy clusters, as the galaxies clusters form over time. So in the early universe, there weren't any galaxy clusters. You need mass to accumulate due to its gravitational influence on the environment around us to build up the structure. So the number of galaxy clusters build up over time and build up over time as more matter is drawn into them. They become more massive and more gas adds to it, so on and so forth. And so we can look at how the abundance of these clusters change as a function of time, which means as a function of distance. Why? Because of the finite speed of light. When I look at a galaxy cluster, that according to the expansion of the universe and the measured rate of that expansion, in other words, Hubble's law,
Yep.
I can see that from the redshift, I note then that I'm looking at a galaxy and light coming from that galaxy that left that galaxy 10 billion years ago. So it's 10 billion light years away at the time that that light was let go from that, or released from that galaxy on its way to us, that sort of thing. So by looking at things that are further away, I'm looking back in time. And I always use the idea, and many people do as well, that a telescope is like a time machine, right? You want to invent a time machine? We already did. It's called a telescope. But the problem with the telescope in terms of time machine is that it only looks into the past. It can't look into the future.
It can't even look to the present.
That's right. So we can look in the past. In fact, your eyes can look in the past. You can look at the sun. If you go outside today and when you're listening to after this podcast is over, of course, while you're listening to it, gives us a thumb up, please, and subscribe if you haven't already. Right. Go outside, if it happens the sun is up, and look at the sun. And the light that enters your eyeball now, at that moment, the present, when you look at the sun, left the sun 8 1/3 minutes ago. So you're not seeing the sun as it is. That moment when you look at it, you're seeing the sun as it was back in time, 8 1/3 minutes. And by extension, if you go out and look at the Andromeda Galaxy that we mentioned already today, and you go tonight and look at it, and you can see the Andromeda Galaxy in a dark site with your eyes. You don't need binoculars or a telescope or anything else. The light left that galaxy about 2.5 million years ago. So you're not seeing the Andromeda Galaxy as it is today. You're seeing it as it was 2.5 million years ago. That may be even before humans existed, or around the time their Homo sapiens are just starting to come along. Who knows, right? I mean, there's some controversy on the exact time scale of that kind of stuff.
Right.
And so telescope is a time machine. So we can look at very distant galaxy clusters and see what the universe was early in its history. And by tracking how the abundance of galaxy clusters change, as you look at ones that are closer and closer, and therefore closer to the present, that gives us a handle on the expansion rate of the universe, which ties directly into the amount of dark energy that existed for different epochs or eras of the universe, right? Time slices. And what this study has shown, and it's consistent with what we've seen with other studies as well, is so far the dark energy seems to be a constant. The amount of dark energy, which we mentioned earlier, 6 × 10⁻⁻10 joules per cubic meter, That hasn't changed, as far as we know today, throughout the whole 14 billion year lifetime of the universe. It's amazing.
Which is pretty amazing in and of itself.
That's right.
It's like, honestly, that's like your car. You put 13 gallons of gas in it, drive as far as you want, and you've still got 13 gallons of gas.
It hasn't changed,
It
right?
hasn't
The
changed.
density. And the other thing is, it doesn't change in different locales. You can look in one direction, you can look directly opposite 180 degrees in that part of the sky, or anywhere you look, it also seems to be the same.
Right. Wouldn't that mean that it seems to be an intrinsic property of space and time itself?
We don't know what the dark energy is, so until we know, we can't
yeah.
comfortably answer those with high uncertainty.
Right.
But the other interesting aspect of all of this is the fact that the density of dark energy doesn't change. Now, what effect will that have on the history of our universe? Well, Robert, let's go to slide number 2.
Slide number 2.
To see this. Now, in slide number 2, what we have plotted here on the x-axis, so the horizontal axis, is really a measurement of looking back into the past. Okay, so astronomers use a letter of the alphabet Z or Z if you're in Canada or in Britain to measure what we call the redshift. And on the bottom, what's plotted here is the log. So this is base 10 log. So the log of 1,000 is 3. The log of 100 is 2. Hopefully you learn about logs maybe in high school.
Here's hoping.
Yeah. And so here we're seeing the log of 1 plus Z.
1 plus Z. Right.
Okay. Now, locally today, that is things that are nearby us, right around us in our face, in our grill. Those are at a redshift of 0. And as we look at things further away, that redshift value increases because the recessional velocity increases with distance to your objects, your galaxies, for example. Mm-hmm. So if you plug in 0 for Z, you get 1 plus 0 is?
1 plus 0 is 0. No, 1.
And what's the log of 1, base 10?
Log of 1 is 10. And base 10? Yeah.
Anyways, let's skip that.
It's what log of 1 is.
What's a 0?
A 0. I was doing it in
Robert,
reverse.
did you learn?
Yeah,
okay.
I did. I was doing it in reverse. I was thinking in the reverse direction. Sorry,
Right.
I was thinking 10 to the first.
So in other words, log of 1 plus Z, when that value equals 0, that's today.
Okay.
So that's the vertical dashed line that you see there in the plot on the right-hand side. Okay? Now, what's shown here, number 1, we have a couple different straight lines, right? Number 1, we have one that's black. Okay, the word matter is written beside us. That represents the matter density of the universe. So as we follow that line and follow it to the upper left, then notice that matter density increases as we go backwards in time. That's essentially what we're seeing along the horizontal axis when we move to the left. So the matter density increases. Why is that? Well, the universe is expanding. So if you run the universe backwards, it becomes smaller and smaller, you would think, unless the universe is infinite extent. And if it is, that means things are just getting closer and closer together. Think of it that way. Even in an infinite universe, that would be true. And so as you go backwards then, the density of matter then would increase.
Right.
Now, how does it change? Well, think of something that's expanding, right? The matter will fill up and occupy the total volume of the universe. And as the universe expands, then the matter density would drop off as 1 over the size of the universe to the 3rd power, 1 over the scale size of the universe cubed. Okay.
Right.
Now, also what's filling the universe besides matter is radiation. In this case, you can think of the leftover heat from the Big
I was
Bang.
about to say, you can think of it as heat.
Yeah, so the early universe we know was very dense and very hot. And one of the observational evidence to support that is the measurement of the leftover heat from the Big Bang, the cosmic microwave background. Now, as you go back in time, the radiation becomes more dense. Why is that? The volume of the universe gets smaller. If you think of some cube of space that's contracting due to the reverse expansion, if you want to think of it that way. Mm-hmm. Or if you're in the early universe and you go forward in time, the universe is expanding, that radiation then is filling up an ever larger volume of space.
It's being stretched out.
Right. So that density, you would think, would fall off as 1 over the size of the universe cube, just like the matter. But it's also becoming redshifted.
which means it's less energetic per photon.
So that means you have to add an extra factor of dilution to the density. So it actually dilutes away as 1 over the size of the universe to the 4th power. The volume effect plus the redshifting effect. So that's represented by the red line you see on this plot. So if you go early enough, that back in time, that is, you go way over to the extreme left side of the plot and then look up horizontally to near the top, notice that the red curve is above the black curve, or the red line is above the black line. That means that the universe was what we call radiation dominated at that very early part of the universe. The energy density of radiation was greater than the energy density of the matter that the universe had.
That would, correct me if I'm wrong here, which I'm sure you will, that would mean that there really isn't a whole lot of matter, that it's all as radiation at that point, wouldn't it? It would be too hot for matter to exist.
Yeah, that's right. And so notice the redshifts that you're at there, right? So this is a redshift of 3,000 where the crossover point happens. This is before the universe becomes neutral. So it's completely ionized at that point. And so the leftover heat from the Big Bang, the photons, they are quickly then run into electrons and get scattered, the Thomson scattering type of processes. And so they don't travel very far before they run into charged particles, essentially, right? Because of the plasma, essentially, the ionized medium that the universe contains at that point. Now, the interesting thing about dark energy and all of this is the blue line that you see horizontally near the bottom here. It's labeled dark energy. Now, if the dark energy is constant, okay, then it can be described by that horizontal blue line that you see there. Notice that near the early part of the universe, the energy density in dark energy is completely negligible compared to the energy density in both the radiation and in the matter. So after redshift of 3,000, so if you go, let's say, to the right after that dot that's labeled Z equals 3,000, then the universe becomes what we call matter dominated. So more of the energy is in the matter rather than the radiation field. Because remember, the radiation falls off quicker than the matter because of the redshift effect, okay? But notice dark energy is completely negligible. It's way down in the bottom part of that plot. And even though it's horizontal, so it's not changing with time, it's a very low level. And you have to wait all the way until you get to, notice, a Z of 0.5. So that's roughly around 2.5 to 3 billion years ago, where now, because of the complete drop-off in the energy density in matter and radiation, now what's happening in the last 2.5 to 3 billion years is that we've entered this new stage in our universe where dark energy dominates.
Right.
So we're in a dark energy dominated era to our universe. Now, what will happen in the future? Well, if the dark energy is an absolute constant like you see here, and that this new result that we showed in the previous slide illustrates, what we're finding is that we'll always remain in this dark energy dominated type of universe. And so the other thing to note here is because the energy density is so low early on in the early universe compared to matter and radiation, that really dark energy had a negligible effect on the evolution of the universe.
Which means things should have fallen together and clumped together.
No, you just had the normal expansion of the universe without really the dark energy kicking in, showing itself, right? It's only till relatively recently that the dark energy has got to the point where it now affects the growth of structure in our universe that we can map it out. And this is why galaxy clusters are very interesting in this sort of study, is because early on, remember, in the universe, there are no galaxy clusters.
Right.
They're forming continuously once the temperature of the universe has dropped to the point where neutral matter can form, that we've entered this neutral, what's called recombination era, this non-ionized universe, if you like. So structure can form. And you need time for gravity to do its thing, to clump together galaxies, to build up, these galaxy clusters. So you need time for that to happen. So by the time galaxy clusters are really forming, dark energy is becoming a significant player, if you like, in this game that represents the expansion of our universe.
So would that mean that there are no more of these galaxy clusters that are forming?
No, they're forming today, but if you go back early enough in time, you can reach an epoch, which the James Webb Space Telescope should be able to probe, were you in the time before galaxy clusters even existed?
Right. But, I was just thinking that maybe it might mean that there's no more forming now because the dark energy is dominating and pushing everything apart.
Yeah, but remember that the energy density is an absolute constant, right?
Mm-hmm.
But matter has clumped together, and that preventing, we're talking about dark energy really having an impact, let's say 3 billion years ago and to the present, and then going into the future. But that leaves you with a universe that's 11 billion years old by the time the dark energy becomes a major contributor.
Right.
So you have 11 billion years of structure to form under gravity when essentially dark energy is negligible.
Right.
So there's lots of structure to form. In fact, things are so close together that the present density of dark energy, which we think is a complete constant, will never change, it cannot overwhelm gravity for things that are nearby, things that are nearby. But going forward into the future, this is the interesting thing. Outside of the local group, right, galaxies are spread far enough that the gravitational force of attraction between our local group and the distant galaxy, then compared to dark energy, right, because of the expanding universe, will become negligible. In fact, all other galaxies beyond our local group, at some point in the future, people estimate this on the order of 50 billion years or so. Whether that's the correct number, I haven't calculated, so let's go with that. All other galaxies are being pushed away so far that they go beyond the observable horizon of our universe.
So we'd see the local group, and that's pretty much it.
And don't forget, in the local group, the giant of the galaxies that are there, there's two of them. There's the Milky Way, our galaxy, and there's the Andromeda galaxy.
And they're going to collide.
And they're going to collide in about 5 billion years. How do we know that? Because you can see that the light coming from Andromeda is blue shifted. So it tells us our relative motion is of approach, not receding.
Right.
And we can calculate based on how far away Andromeda galaxy is and how fast we're moving towards Andromeda, relatively speaking, that we should start to merge in about roughly 5 billion years. Right. Now, that can change a little bit if there's any sideways motion. Right. So we use things like space-based telescopes like the Hubble that's been up there for several decades, since I think around 1990, for example, and take images of the Andromeda back then compared to what you take today, let's say, and we can't perceive any sideways motion to the Andromeda galaxy. So as far as we know, we're on a direct head-on collision course. Okay? And so that means we will begin to merge in about 5 billion years. And the result of that merging, we expect would be something that would be like an elliptical galaxy. How do we know that? Because we can run simulation with huge number of particles all interacting by gravity, two different galaxies, like two spiral galaxies, merge them together. When things dynamically settle down after over 1 billion years, it looks very much morphologically or like classification-wise like an elliptical galaxy.
Right.
So, 20, 30, 50 billion years from now, these are the kind of time frames we're talking about, our local group might be just one giant massive elliptical with some maybe low mass galaxies, what we call satellite galaxies in orbit around us, this kind of thing. But there'll be no other galaxy observable in that universe. So if you are a life form that arises, let's say 50 billion years from now, on a planet that orbits some star, and you look out with a telescope, right, and you see what's beyond, the galaxy that I live in, the answer is nothing.
Right.
So you think the whole universe was just your galaxy. That's kind of the idea we were prior to the 1920s.
Right.
But the interesting thing in all of it is, can we even tell that we live in a universe that has the characteristics or properties that we measure today? So let's deal with the first thing we looked at, the expansion of the universe. If there's no other galaxy in our universe, how do you measure motion relative to something else?
You can't.
You can't. If you are flying in a spaceship and there's nothing around anywhere in the universe and you're going at a constant velocity, so there's no acceleration, right?
You feel nothing.
How do you know how fast you're going? And it doesn't even make sense to ask that question because you'd say relative to what, right?
Right.
There's nothing else you can measure relative to. You see? Right. So therefore, there's no other galaxy in your universe to measure the fact that the universe is expanding. So that observational evidence goes away. You don't have that. Okay? So what else do you have? Well, we have the leftover heat from the Big Bang.
The CMB.
But because that fills up such a huge volume of space with this accelerated expanding universe due to dark energy, that CMB photons, they get hugely redshifted. So if you like, they become so redshifted, they become almost impossible to measure.
The noise would overcome any signal.
Yeah, so you don't. There's no leftover heat. You can say it as the temperature of that leftover heat approaches zero, absolute zero.
Right.
It approaches absolute zero. So that evidence that we have today, that was discovered in 1964, is gone.
It's gone.
Okay. So what else do we have? Well, the other thing that we use to support the Big Bang Theory, and it's a theory, not a hypothesis. Why? Because there's lots of observational support for it. So it's migrated from the hypothesis category to the theory class, okay?
Right.
Is the fact that the early universe, that is the distant universe, looks very different than it does today. Or when we look at things like 10 billion light years away and so on, there are a lot more irregular type galaxies, a lot more interacting galaxies. Early in the universe, there's a lot more active galactic nuclei, as we say, and so on. So the universe looks just different. It evolves, not biologically. That's another issue. But the universe itself changes. It's not the same, right?
Yeah.
That's totally consistent with the fact that the Big Bang happened and at the early moments of the Big Bang, the universe was very dense and very hot. The universe should change with time. Okay?
Right.
It should evolve in that sense. Okay? But if you don't see any other galaxy, how can you see the early universe if you're 50 billion years in the future? You can't. So that clue goes away. So we lost the expansion of the universe as a pillar for the Big Bang Theory in the deep future, right? Far future. We lost the measurement of the leftover heat from the Big Bang. We lost the fact that you can measure the early universe and know that it's different than locally around us today. There's only one thing left. What's that one thing, Robert? Can you figure that one out?
Not really. I'm thinking dark energy would still be there, but you'd have to know what it was and that it's there.
And how could you measure the accelerated expansion of the universe? There's nothing to
There's
measure it
nothing there
against.
to measure it against. Right.
So that's not it.
Yeah.
What other major pillar or foundation post, if you like, supports the Big Bang? Not the expansion, not the CMB, not the fact that the universe evolves. What's the fourth one I'm looking for?
The quantity of elements.
Exactly. Big Bang nucleosynthesis.
Right.
In other words, where the heck did the hydrogen comes from?
Right.
Okay? So if you live on a planet that's orbiting a star, you look at the stars around you in your own galaxy and you figure out all of stellar evolution, which you can do, okay? Then you know that the first generation of stars had essentially hydrogen and helium with a trace amounts of some other things, if you even could figure that out.
Right.
In other words, most of the heavy elements came through, formed inside of stars, or they formed during supernovae or the collision of neutron stars, these kind of things. But there has to be hydrogen to begin with to form the very first generation of stars. Now, where did that hydrogen come from?
That's kind of a question we're still asking, except for the fact that we know that there was a time, we can see that time, where it was the matter was hydrogen dominated.
Yeah, so we know today that the hydrogen came from the early universe. In the heat of the early universe, the hydrogen was cooked.
Right.
In the first 1,000 seconds of the universe, right, that's where we created hydrogen, helium, and trace amounts of lithium, boron, and beryllium. These kind of things, okay? And so therefore, the universe, if you think of normal matter or excluding dark matter, that universe by mass was about 74% hydrogen, roughly 25% helium, and then you have 1% left of everything else, which is these very minor kind of stuff.
Right.
All the other heavy elements like iron or carbon that's in your body and stuff, they all came inside of past generation of stars. But the Big Bang itself, the creation of the universe, formed the hydrogen, right? Now, it's interesting. How do we know the details of that? Well, the joke I always use is, imagine you go home tonight, you want to cook a 16-inch pepperoni pizza. You turn on your oven. It's an electric stove, right? Electric oven.
Okay.
You turn on your oven, you preheat it. You get it to the right temperature. You put that pizza in. You're all waiting for it. You can't wait for it to be cooked, and so you're starving, right? You put it in the oven, and then the power goes out. Boom. And then you say to yourself, I just hope that oven is hot enough and it doesn't allow enough heat to escape, that by the time, maybe after some period of time, maybe 30 minutes, maybe an hour, that it will be enough heat trapped in that oven that it will cook that pizza to the point where I can eat it.
Right.
Well, that was the same as the universe, by analogy here. The early universe was very hot, but because it was expanding rapidly right after the Big Bang, you only have a certain period of time to work with that you can forge these elements, that you can make these lighter elements in a periodic table like hydrogen and helium. Because if you wait too long, the universe expands, the temperature drops, then favorably, energetically, probability-wise, you can't form any more hydrogen or helium. And so based on what we think the expansion rate was all about, then we know that within the first roughly 1,000 seconds of the Big Bang, that's when conditions were right to allow us to form these light elements.
Right.
So where did the hydrogen come from? It came from the very early, hot, dense universe. It was cooked in the fires of the Big Bang. Now, if you didn't know a Big Bang existed, if you thought the universe you look around us today is the same one that's always been like that, how would you solve that mystery of where the hydrogen came from? So for a distant future, 50 billion years from now, right, that life form is going to wonder where the heck did the hydrogen come from that formed the first generation of stars. And they don't have the Big Bang to cook it. There is no oven.
Right.
So if they're really, really smart, they might say, well, maybe in the distant past, the universe was altogether really dense and really hot. It has been expanding ever since. In fact, now what we see today is just our galaxy. All other galaxies have been expanded beyond our observable horizon. We just can't see them. Maybe they could posit it out then. Who knows?
Who knows? I don't know that I'd lay my very good odds on it. And somebody wouldn't just say, well, I guess the hydrogen was just here. But, we would hope that whatever life form is there has actually built up from when the universe wasn't so expanded. But
right. And if we use science saying it was just here, that's a cop-out.
Right.
We don't do that in science. That's ugly.
I agree. That's
right?
ugly.
That's ugly. We want to figure out.
We want to know why and how. So.
Exactly. Now, if you go back to slide number 2,
okay.
Here's another point that I'd like to make here. Now, because the energy density is measured to be a constant, as far as we can tell today, an absolute constant, it's not changing with time, the universe is changing. And one way it's changing is it's getting larger. The universe is expanding.
Right.
So in that sense, the volume of the universe is constantly increasing. And yet the energy density is an absolute constant. So the total amount of dark energy in the universe is getting larger. There is no conservation of energy.
Ooh.
Yes, I am a physicist trained. Okay?
Yeah.
I can say that the conservation of energy breaks down in an expanding universe.
Right.
That's
Now,
the problem.
And people say, oh, well, that's overturning all of physics. The thing is conservation of energy has always been related to a system. You define a system, and energy, as long as you're not inputting it from outside, energy is conserved. But if your system is large enough, does that really hold anymore?
Well, and then if you think of the general theory of relativity, which is our best theory on large scales that describes gravity, there is no violation, there is no problem, in other words, if you put it this way, to violate energy conservation in an expanding background in which is the stage in which matter and things exist. If that background is expanding, right, then there's nothing in there that says you're violating general relativity because of that. It's okay.
Right.
That's really the point. And several people have made this point that in an expanding background, overall, the conservation of energy then is violated. But in general relativity, is what I'm saying here, that doesn't go against that theory. That is consistent with the general theory of relativity.
And again, I will point out that to all your physics students out there, that doesn't mean you can ignore conservation of energy, because you have to be on the scale of the universe for it to be violated.
Right. And that's why you could use, as you mentioned already, well, when we think of conservation of energy, imagine a closed system, right? And you're looking at a closed system and there's energy missing. And then you might wonder, well, my system's not really so closed after all. Some has leaked out. Maybe it's the emission of some particle that carries away energy, whatever.
Right.
So then you have to broaden out that boundary to make sure that you encompass everything, so that the bookkeeping then matches and that the conservation of energy is satisfied.
Right.
But if you keep doing that on larger and larger scales, eventually you get to the size of the universe, and then you could argue here, well, then doesn't that mean dark energy violates the conservation of energy? Maybe I should grow out my boundary a little further, right? But you can't, because the universe by definition is all that there is,
Right.
you see? So you get trapped. So you're always comparing stuff locally, some experiment that you're doing, to around you, right? Outside your immediate surroundings, looking for violation of conservation of energy, or at least showing that it still, applies or whatever.
Right.
But at some point, when you use the whole universe as your playground, you can't go outside of the universe.
Mm-hmm.
You got nothing to compare it to, you see?
Right. And I guess that's really the point, is there's nothing to compare the universe to. It's comparable only to itself. So there's no 0 point, if you will.
Right. But the other thing, if you want to get a little technical, it's the fact that we live in a universe that's expanding. Right? And from general relativity, right, the background is expanding, then there is no rule that says you can't violate the conservation of energy. And dark energy is a good example of what this violation means in more modern sort of era today, what we mean by violation in this sense. Okay?
Yeah.
So whether you like it or not, it doesn't matter. That's the way the universe is.
Right.
Right? The universe is the universe is the universe, whether we like it or not.
Our question then becomes, why? And why is it that way, and what's going on?
Exactly, and that begs the question, then what the heck is this dark energy? Where did it come from? Why is it the amount that it is today?
And hence why I asked my question towards the beginning of, is it then intrinsically just a part of space-time?
Well, people try to figure this out. What's our best sort of formalism that we look at if we're trying to figure out the different energy that's in the universe is quantum field theory.
Oh, okay, yeah.
That's a fancy term that basically takes all of quantum mechanics and puts everything together, relativistic quantum mechanics and so on, and applying to where things are treated as waves. You have energy fields, or whatever you want to call them that way, right? So there is a field for an electron, there is a field for the proton, which would be individual quarks, of course, technically, right? These kind of things. And so quantum field theory at its basic fundamental level, when you try to use quantum field theory to predict what would be the dark energy of the universe, you get really two values. That's what most people get, right?
Okay.
And those two values...
Infinite or 0?
Yes, exactly. You get 0, or you get something like, and this depends on the actual calculation you do, so take it a little bit with a grain of salt. The amount that we measure today multiplied by 1 followed by 120 zeros. As people say, that's not even wrong. It's so far off, right?
Right.
You see? It's way off, right? So then people just naturally assumed it was 0. But since 1998, we no longer can make that assumption. We have to face the reality that our universe has this dark energy. So we have to figure out then, why isn't it 0? And why isn't it this 10 to the 120 power times greater than what we actually measure?
Right.
Why is it the value we do measure, this value of 6 times 10 to the minus 10 joules per cubic meter? Why is it that value? And if our most basic fundamental laws of physics, the quantum field theory, the best that we have today, if it can't explain it, which people have been working on this problem for 25 years now, theorists, and haven't explained away, haven't shown why it's the case, right? So if you can't explain it with quantum field theory, then that tells me that this stuff, physics, at a deep fundamental level, is not complete.
It's not
We're
quite
missing
right.
something.
Right.
You see, and that something maybe...
Now, I will mention it's a little something.
Yeah, well, that something may
something.
explain why we have this dark
Yeah.
energy and the value that it has. That's the important thing,
Right.
You see? Because we can always say it has dark energy, right? I
Right.
mean, you can get that out of quantum field theory, as I mentioned. But it has such an extreme value that as soon as the universe formed, if it had that amount of dark energy, it would just, expand so fast, nothing would ever form. There would be no stars, no planets,
Not even any protons.
no galaxies, no clusters of galaxies,
Right.
no life, no us. You see?
Right.
Obviously, that is not the type of universe we live in.
Right.
We live in a universe that has a little bit of dark energy, right? In fact, our universe almost demands that amount of dark energy based on the observations that we see of structure around us. That gets back into the discussion where we can use galaxy clusters spread over certain range of distance volume of our universe and use the abundances of those galaxy clusters to puzzle out what is the strength of the dark energy and has it changed with time. So the type of universe we live in and what we see around us, we need dark energy. We need it.
Right.
You can't, the evidence for it is overwhelming now, right? You'd never be able to explain the universe we live in if we don't have it.
Right.
So the question has changed then, not from do we need dark energy or what can we measure its influence? Yes, we can. The question now is focused on, of course, what is the dark energy and why does it have the strength, if you like, the energy density that it has, that we measure?
Right.
That's the fundamental question today.
Sounds like a plan.
Sounds like a plan.
Join us. Come win a Nobel Prize.
Exactly. Now, we always leave you with a quote. So we're going to leave you today with a quote from Richard Feynman, one of the most probably famous physicists in our generation anyways, Robert.
Yep.
And the quote that we're going to leave you with, there are many quotes from Richard Feynman. Some you can say publicly.
Some you can't.
Some you can't. This one you can say publicly. In fact, it's related to what we are talked about today. So the quote is, it doesn't matter how beautiful your theory is, and it doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong.
Dun, dun, dun.
Here you go. So thank you for listening. If you're, like Robert mentioned, if you would like to get more involved in physics and astronomy and astrophysics or science in general, especially if you are just starting to think about a college career, please consider the University of North Dakota. We'd love to have you here. There are lots of exciting programs going on here on campus. Now, our next podcast will be Tuesday, May the 16th, always at 3 p.m. Central Time.
Indeed.
And then thank you very much for watching.
Thank you, folks. You'll have a great day.